5.8, Analyze graphs and polynomial functions. So first we're going to talk about end behavior of polynomial functions. So what I mean by end behavior is if I have a polynomial graph and they end up being these kind of squiggly looking things, the ends would be as you go to the left and as you go to the right. And when we talk about the ends, if we're talking about going left or going right, we're really talking about what x is doing. And the behavior is what ends up happening for y. So as we go to the left, what's happening for y? As we go to the right, what's happening for y? So that's our end behavior. It's these spots where I put those arrowheads to show that my graph goes on and on forever. So first we're looking at when the degree is odd. So to connect that back to something we already know, think about how a linear function is really x to the first power that's odd. So if I have a slope that's positive, my line goes up. If I have a slope that's negative, my line goes down. And that's what we have here. So when we have odd degrees, my ends are going in different directions on both of them. And the one that starts with a positive leading coefficient is going up, and the one with a negative coefficient is going down. So again, we're trying to relate that back to a linear function because that is an odd function. It's first degree, first power, that we already have experience working with. So next we look at even functions. So with even functions, both of our ends are going in the same direction for y. So for that one, I want to connect it back to, if I'm talking about even, I want to think about a quadratic. So I know if I have y equals a positive x squared, my y is going up. If I have y equal to a negative x squared, my y is upside down. And that's what we see here. So when we have a positive leading coefficient, my graph is going up. When it's negative, both ends are going down. So again, with odd, the graph is going opposite directions and up for positive, down for negative. With even, both ends of your graph are going the same direction. And up is positive, down is negative. So now we're going to look at degrees of polynomials and what the basic shape of the graph is. So we already wrote up above linear functions we know are just a line. And I'm going to draw a few different lines. Lines can look lots of different ways. We should probably also add in if it's degree 0. That's when I have a constant. And that is like y equals a number. It's a horizontal line. Second degree is a quadratic. And we know all about parabolas. We could have a big wide parabola. We could have an upside down parabola. We can have a skinny parabola. All different shapes. So what I want you to notice here is when I have a linear graph, I just have a straight line, I have 0 turning points. A lot of times students will talk about like the humps on a graph. A linear doesn't have any. Quadratic will have one of those loops or humps. So there'll be 1 turning point. So it's literally this point right here where I'm going down and then I'm going up. That's a turning point. Or I have a turning point right here. The graph is going up. I get to that turning point. Now I'm going down. So third degree is a cubic graph. And you might expect this pattern continues. If first degree has 0 turning points, second degree has 1 turning point, then a cubic graph will have at most 2 turning points. So if it's positive, it could look like this. So here's my 1, 2 turning points. It could be a little more flattened out, more like that, where it almost just looks like kind of one point of inflection in the middle. It could be upside down, and they could be different lengths like this. So all different, it could be stretched out. So all different shapes for cubic graphs. But again, at most 2 turning points. When we look at fourth degree, that will be at most 3 turning points. So if it's positive and both ends are up, we'd have 1, 2, 3, something like that, kind of like a W. Or it could be a negative, so it's upside down. It could be more like this, where it almost is like, I don't know, like a straight line almost between those two. Or it could be a tall, skinny parabola kind of shape, but very tall and skinny. Or we could even get something like this, where one of those humps is really small and the other one's really big. So those would all be fourth degree graphs. When we look at fifth degree, our pattern continues. We have at most 4 turning points. And the ends of the graph go in different directions again. Here's 1, 2, 3, 4 turning points. Let's count them. 1, 2, 3, 4. Yep. Or it could be upside down. 1, 2, 3, 4. So lots of different shapes for these. So for example 1, just by looking at a graph, we're going to guess what the degree is and what is true about the leading coefficient, which means really positive or negative. So let's look at our turning points. Both ends are down. That tells me it's even. And it tells me that I have a negative leading coefficient. And I have 1, 2, 3 turning points. So if I look at a graph that's degree 4, it's at most 3 turning points. That's probably what it is. So we'll write degree 4. And it's negative. For example 2 on the back, we want to go ahead and graph. And before we go ahead and graph this, I want to add something at the bottom of our notes that we did yesterday in 5-7. So yesterday we looked at how if we had a factor to an odd power, and remember this could just be the first power, right? First power is odd, and then it wouldn't have a power written there at all. It would be understood. If n is odd, it's going to cross our graph. And if I have x minus k to the nth power, but n is even, then it's going to bounce. And we did draw an example of this yesterday, so let's look at that again. So here's my xy axes. Here's a graph coming down that's going to bounce, and then it's going to cross. So again, this is a bounce, even power, and this is a cross. So now we're going to look at actual graphing and using this. Using the shapes that we just came up with, we're going to put it all together. So for example 2, I have an x, and then this x is being squared. So that tells me I would have x cubed. I'm going to have degree 3. And I have a negative. So I have kind of a guess of the shape of my graph. All right, now I need to go through and figure out my x-intercepts and my y-intercepts, or y-intercept. So to find my x-intercepts, I just have to look at this and solve it. So I would have a negative 2 for x, or a positive 1. Now negative x plus 2, that factor is raised to the first power. There's no power there at all. That's odd, so it's going to cross at negative 2. But at 1, I have the power of 2 for x minus 1 squared. So that is going to be a bounce. That's an even power. And I'm going to erase this work because it looks really messy here. To find my y-intercept, I would put in 0 for all the x's. So 0 plus 2 is 2, so it's a negative 2 times 0 minus 1 would be a negative 1 quantity squared. So negative 2 times 1, negative 2. So now I have to go through and graph these all. So let's see, we're going to graph x-intercepts at negative 2 and a positive 1. And we'll graph a y-intercept at negative 2. And then we know the shape of our graph, and we know it's going to cross at negative 2 and it's going to bounce at 1. So it's going to start up here. We're going to cross, We'll go through our y-intercept, we'll come up and hit that and bounce and go back down. And I really could have made it look a little bit curvier at 1, but it's hard to do when you're making your graph so small. If the scale was bigger, if I had more space between the squares, that would be easier to write. But that's the kind of graphing we're going to be doing. So we're using what we know about graphs and shape and negative or positive. We're finding just a couple points, our x-intercepts and our y-intercepts, and then we're going from there. So to look at turning points of polynomial functions, and we kind of talked about this earlier, but now we're going to actually get some math language down here. The graph of every polynomial function So the graph of every polynomial function of degree n has, at most, n minus 1 turning points. And that's the pattern we found earlier. Remember, we started out with linear graphs. Linear graphs we knew had no turning points at all, so that was degree 1, had 0 turning points. We knew that quadratics, which is degree 2, had only 1 turning point. So we kind of built everything off what we already knew. If a polynomial has n distinct real roots, so distinct means they're all different numbers, we don't have anything repeated, and they're all real, we don't have any imaginary, then its graph has exactly n minus 1 turning points. So for our final problem, we're going to look at a big complicated math problem in the notes here that kind of put everything together. It's 4th degree, so oh my goodness, we've got 5 terms. There's no way I can factor it. But I do want to find x-intercepts and y-intercept. So in order to factor then, I'm going to have to use p over q. I'm going to have to go through and do that whole process to help find those zeros. Remember, the zeros are really x-intercepts. So fortunately, my leading coefficient is 1, so q is 1. So then p over q would be plus or minus 1, plus or minus 2, plus or minus 4. And then I'm going to try some values. So I will put 1 in here. So 1, 4, 3, -4, -4. Those are my coefficients. Do my synthetic division, bring down 1, multiply it, write it underneath, add, multiply, add, and we found our first zero. So now I'm going to work with my depressed equation. Depressed equation is x cubed plus 5x squared plus 8x plus 4 equals 0 now. And because my last, my constant term is 4, then p over q is still the same, plus or minus 1, plus or minus 2, plus or minus 4. So normally I would try 1 over again, but I'm thinking about how these numbers are all positive, the 1, 5, 8, 4 are. And if I have all positive numbers, and this whole process is just multiplying and adding when I do synthetic, I'm not going to get a 0 out of that. I'm going to have something that's negative. So I'm going to try -1 instead. So I would actually not guess any positives on this, because when I bring it down by 1, I multiply it, I write it underneath, I'm adding it, I'm just going to keep getting bigger numbers, because 1, 5, 8, 4, all of those are positive. So I'm going to try -1. Bring down 1, multiply it, let's see, 4, -4, 4, -4, 0 again. So now we will take what's left, 144, sorry. So I started out with 4th power, I found a 0, I was down to cubed. Now I will be down to x squared. So x squared plus 4x plus 4. And I can factor that as the quantity x plus 2 squared. So I'm already thinking of a bounce, it's an even power. I would square root on both sides. Absolute value of x plus 2 equals 0, but there's no plus or minus 0, so it's just x plus 2 equals 0. So x equals -2. So I've got my equation solved. So let's go through and find our x-intercepts and just list them all out here. So our x-intercepts were 1. We know that 1 was a 0, -1, and then -2. And let's remember that 1 was a cross. 1 and 2 are both crosses. And -2 is a bounce because that's the factor that was squared. So there was only one answer of 1, there was one answer of -1, but -2 happened twice. Remember, the fundamental theorem of algebra says 4 solutions here. And we get that because -2 had a multiplicity. It was a repeated solution. It was squared, so it was repeated twice. So I really have 1, 2, 3, 4 solutions here still. The other thing I need is my y-intercept. So my y-intercept, I would get it by making all my x's 0. So I would have 0x to the 4th. This would be a 0x, 0 cubed, 0 squared. So everything is going to cancel out except my constant term, which is -4. So now I'm going to plot everything again. My y is -4. My x-intercepts are -2, -1, and 1. So this graph is really kind of jammed up around the origin. Because it's degree 4, I know both ends go in the same direction. It's positive, so they're both going up. So it's going to be some kind of shape like this, like a W. So I'm going to have to start the graph here. It's going to bounce at -2 and come up again, and then cross at -1, go down through the -4, and then back up through 1. So my graph would look something like this. So these are not perfect graphs, but we should have the x-intercepts, we should have the y-intercept. And I am noticing that I completely spelled the word remember wrong. So let's fix that really quick, and then we're done with our notes. It's kind of funny to not remember to spell remember correctly. And we're all set. Thank you.